Hello everyone, welcome back. We are starting chapter 7 today, and I actually already made this video once, but I neglected to hit the record button. So I'm going to salvage about maybe a quarter of the things that I've already written down. We can talk our way through them, but then we'll also fill in the gaps with everything else that I need to talk about. And so with chapter 7, if you haven't realized it at this point, this course is very, very comprehensive. Everything that we learn in one chapter gets carried on to the next, and to the next, and to the next. And so all of the kinematics that we did in chapters 2 and 4, all of that got combined together with the vector materials from chapter 3. We started using all of that with our chapter 5, chapter 6 material discussing force, and force was what allowed us to actually find out why a mass is accelerating at the rate that it does. And if we had multiple forces acting on a mass, then we could take a summation of those forces to describe the final actual net acceleration of that mass. But my preference for these is to take individual summations in the x and the y directions, and then that will tell us what the x and y acceleration values of our object are going to be. And once we know the acceleration of an object, we can apply that back to our kinematics. And the kinematics said that as long as you had 3 pieces of information, you could solve for the other 2. And so that's what we're going to continue doing. We're going to basically continue using kinematics, except we're going to hide the kinematics in a new term, or let's just call it a different approach to solving the problem. So up here I have a diagram that shows a mass with a force applied to it. And inside that force expression is hiding the acceleration term. As we apply that force over a certain displacement d, the mass will change its velocity from some initial value to a final value. And so I've got 4 of the 5 kinematic terms already on the screen. Of the 5 kinematic equations, each equation only has room for 4 pieces of information. Now I'm specifically leaving out the time, and I'll explain why a little bit later. But if we take these 4 kinematic equations and look back in our notes to the appropriate, or if we take these 4 kinematic variables, excuse me, and we plug them into the kinematic equation that includes those 4. That is this one. Now the only difference between this and the values that I have up in the diagram here are that I'm using d as the displacement vector. So I'm just going to take delta x and I'll replace it with d. And this was one of the 5 kinematic equations. The one condition that we had for those kinematic equations to work, at least in terms of deriving them, was that we had to have a constant acceleration. And this was okay, especially considering things like gravity, which is basically constant here at the surface of the Earth, but also as long as we had any kind of force that was constant, or uniform? Well, we don't always have to have uniform forces. We can have forces that are variable. And these are forces that are going to change with respect to some other variable in the system. And it's reasonable to say that a force could vary with respect to time, but we could also say that a force could be measured as changing with respect to position or even velocity. There's a lot of different ways that we can measure changing rates in systems. But regardless of how the force is changing, if the force is variable, then something over on the other side of the equation also has to be variable. It could be the mass, it could be the acceleration, it could be both. In the case of a changing mass, a really good example of a system that would have a changing mass would be something like a rocket. As a rocket blasts off, it expels some of its mass in the form of exhaust. And so the mass of the rocket changes. If the mass of the rocket changes, then we could end up with a variable force, but we could also end up with a variable acceleration. Given that this is an introductory course, we want to do our very best at maintaining a uniform mass for our objects. We don't want our masses falling apart along the way. And so that means there's going to be a variable acceleration whenever we apply this variable force. So what does that mean in terms of the kinematics? Well, even though our derivations required us to use a constant acceleration, there's really no reason that we can't use a variable acceleration in our equations. But just in case, we're going to try that new approach that I mentioned earlier. And that new approach is going to be what we call energy. Chapter 7 and Chapter 8 are going to be our introduction to energy. We're going to have different types of energy along the way. In Chapter 7, we start with kinetic energy and work. We'll define what those are here in a moment. Then we continue into Chapter 8 with potential energy and the conservation of energy. Now, let's try getting some definitions for a couple of these new terms, and then we'll come back and we'll see why we want to use this new approach of energy as opposed to the kinematics. And if anyone else can find a good definition of energy, I welcome you to contact me and let me know. But so far, I have not found one. The book's definition is kind of vague. I've Googled the definitions for energy. Everything out there is kind of a flimsy definition, and it's just not very helpful. So what I have here is my version of the definition of energy. It is an intrinsic property of the object that allows for work to be done. All right, well, we see the word work in there, and work was the other major topic that was going to show up in this chapter. So let's get a definition for work. Well, work, by definition, is a change in energy. So we've just provided ourselves with a circular definition. We have some intrinsic property that allows us to do work. Well, what is work? Work is the change in energy. But what's energy? It allows us to do work. So far, nothing is helping. But along with that basic definition for work, a change in energy, it's worth mentioning that there are two different ways that energy can change. One way is to transform the energy from one type to another. And as we saw up here, we already have two different types of energy that we're going to be exploring. There's kinetic energy and potential energy. So it is possible to transform one type of energy into another. And the way that we accomplish that is to do work. Well, what's work? It's the change in energy. Okay, well, that's still not helping. The other way that we can change energy for an object is to transfer it from one object to another. And if we transfer energy from one object to another, that means that one object is losing energy while the other object is gaining energy, but that's still a change in energy. So that still justifies the definition of work. Well, what about that term intrinsic? What does that mean? Well, intrinsic refers to internal. So this is some internal property of the object that allows for work to be done. Again, we're still kind of going in circles in terms of that definition. But the one place where I've seen terms like intrinsic and extrinsic come up quite often are in areas like psychology. And I know that's probably the last thing you were expecting to hear about in your physics class, is talking about psychology. But just to kind of give you a side example here, at the end of this semester, when we finish up this class, you are going to be expecting an extrinsic reward from me. And that extrinsic reward would be a grade for all of the effort and work that you've put into this class. And you're hoping that that extrinsic reward will be an A, maybe a B. Anything less than that probably wouldn't feel like a reward, but you have something to show for all of the effort that you put into the class. But the reason that this is extrinsic is because it is external. It is a reward that comes from outside. It's coming from me. But then you have intrinsic rewards. Well, what would an intrinsic reward be? What reward could you give yourself for doing well in this class? And those intrinsic rewards might just be something as simple as feeling good about yourself. You know, maybe having a little bit of pride in getting an A in the class. You give yourself a little pat on the back. Well, these intrinsic properties, you know, pride could almost be related to like a feeling. And how easy is it for you to define a feeling? Not so easy, is it? Well, likewise, with energy being an intrinsic property, it's not so easy to define. But we can assign some math to this. We can assign some units. We can measure energy. We can measure how the energy transfers or transforms between objects. And as long as we can do the math, well, then I guess it really doesn't matter if we have a vague definition of energy. The major difference between these analogies is that I don't really know that you can measure quantitatively a feeling, but nope, figure it out. Maybe you can make yourself a nice paper to publish there. Well, it's at this point that in the book, if you're following along, the author says, okay, here's the first energy that we're going to use. It's kinetic energy. This is the energy that is associated with motion, and here's the equation. Go play with it, have fun. We'll come back and talk about where this equation came from later. And literally about 2-3 pages later in the chapter is where they actually derive where this equation comes from. Well, I would rather see the derivation of where this equation comes from before we run off and play with it. One thing that we can do is we can put together some units for energy. I don't think I already had the units listed up here. They're going to be joules. But let's talk about what a joule is made of. In this equation, we have the mass of the object, which would be measured in kilograms, and we have the velocity of the object squared. Velocity is meters per second, but then we have to square that, so we get kilogram meters squared over seconds squared, and that looks deceptively like a Newton, except a Newton is a kilogram meter per second squared, and we have an extra meter. Well, okay, that means that the total unit that we are calling a joule can also be represented as a Newton meter. And what have we been using to measure with newtons? Well, we measure forces with newtons. What have we been measuring with meters? Well, length, displacement. Okay, let's go back up to the picture that we had drawn before. What's happening in this picture? Well, I have a force which is being applied over a certain displacement. And so that means that there will be some kinetic energy that is going to change. And the definition that we had for kinetic energy was based on the velocity of the object. So I guess that means that in terms of our definition of kinetic energy, we could have a kinetic energy associated with the initial velocity of the object. We could also have a kinetic energy associated with the final velocity of the object. But again, we don't even know why we're using this equation yet. So let's figure that out. Remember that kinematic equation that I wrote down up here? Well, let's take that and let's apply it to our system. We have our kinematic equation that describes how our velocity is going to change based on the acceleration and the displacement of our object. The one thing that is missing from all of our kinematic equations is the mass of the object. It wasn't actually until chapter 5 that we brought the mass of the object into these expressions. That's what I want to do with this kinematic equation. I want to introduce the mass. Now, I can't just include the mass somewhere without changing the equality of the equation. I can't change the equation itself. So the only way that I can maintain the equality is whatever I do to one side of the equation, I have to do to the other. So I could add mass to each side, I could subtract mass from each side, I could multiply, divide. There's a lot of different options, but I'm going to multiply both sides of the equation by mass. And that means every term in the equation will get a mass. Now, your first instinct is to go through and factor out the mass, but don't do that. We want the mass to be in there. The next thing I'm going to do is I'm going to go through and divide through by this 2. And why are we doing that? Well, why not? I mean, as long as we do the same thing to both sides of the equation, we maintain the equality. But as I do that, right here, I get 1/2 the mass times the velocity squared. Well, that's the final kinetic energy expression that we just came up with up here. Similarly, we have the initial kinetic energy expression. And we have this leftover stuff that spells mad. Well, no, I'm not angry, I'm not crazy, but all that extra stuff there, if I move the kinetic energy terms over to the same side, I have final kinetic energy minus initial kinetic energy. Anytime I have final minus initial, that is a delta statement. That is a difference. This is delta K. And this is a difference in kinetic energy. Well, our definition for work does not distinguish between what kind of energies we're talking about. We're going to have different kinds of energies. Right now, the only one we have to play around with is kinetic energy, but we now have a change in energy, and that means that work has been done. But what does this change in kinetic energy equal? It equals that leftover stuff that we had in the equation. What happens if we combine mass and acceleration? Well, that makes force. And right there we've got displacement. And we've already said that the units of force and displacement equal the same units of energy. So what we have now is what we call the work energy theorem, or W.E.T for short. And what this says is that if we apply forces to our mass over a certain displacement, that work will cause a change in the kinetic energy of our object. Specifically, we have, if you remember, the acceleration, which is hiding inside that force term. And that acceleration is going to change the velocity of the object. Well, we have velocities hiding inside those kinetic energy terms. If we change our kinetic energies, we change our velocities. This expression says that the only way that we can change our kinetic energy is if we do work. Okay. Well, how many different forces can you have applied to a mass at any given time? You could have one. You could have more than one. You could have 2, 3, 4. We've already seen in chapters 5 and 6 that we can have a multitude of different forces acting on a mass at the same time. But it's not until we add up all of those forces that we get the final information that tells us how we're accelerating. And it's that final net acceleration that is ultimately going to tell us how our mass is going to change its velocity. So we can't just limit ourselves to calling this work. It has to be the net work that is done. And just like with net force, net work implies that we're going to have to add up all the work done by all the forces in the system. Okay, well, we've been preparing for this. In chapters 5 and 6, we've been working on taking the summation of forces. Now that we've done that, we can apply our net force to the displacement of the object. And that should tell us what the net work is. Net, not Ned. Okay, well, there's two ways that we could accomplish this. We could go through the process of finding a net force, and then we could apply that to the displacement that our mass is traveling through, and that would give us the net work. Or we could take each individual force times the displacement, and given how many forces there are in the system, each force would do an individual amount of work, which we could then add up to make the net work. The only question here is, which one would be easier for us to do? In my experience, it's this right here. It might look like more work, but keep in mind that doing a sum of forces means adding up vectors. You might have to break those forces up into components, etc., put them back together. So the work involved is probably pretty even between the two. But my reasons for taking this approach here is because we can see individually how much work each of these forces is going to do. And if we go back to the units, we said our energy was going to have units of joules. The work is also going to have units of joules. So work is a change in energy. Work is measuring a change in energy. But what is energy? Is it a scalar or a vector? Because that's going to tell us how we have to treat things like kinetic energy and work. Are these going to be scalars or vectors? Well, the easy way of answering that question is to ask, what physical direction do these values need to be pointing in? So, what direction does work point in? What direction does energy point? And if that sounds kind of confusing, that's good, because energy does not have a direction associated with it. Both of these are scalars. They have to be. Well, looking at this term right here, we've got force and displacement. Well, force and displacement are both vectors. How do we take two vectors and turn it into a scalar? Excellent question. And this was something that we kind of glossed over in Chapter 3. In Chapter 3, we had all of our vector math, adding vectors together, multiplying vectors. And the one thing that we never quite finished in terms of our discussion was what happens if you try to multiply two vectors together. And there were two options for multiplying these vectors together. We had something called the scalar dot product, or dot product for short. And we had the vector cross product, or cross product for short. I prefer to use the full name for each of these because the word out front tells us what we're going to get as a result. of that particular multiplication. For the scalar dot product, we get a scalar quantity. For a vector cross product, we get a vector. Now you have probably seen or used a dot product before, maybe back in college algebra or trig, and at that point you probably saw how we're going to evaluate the dot product. We're not gonna worry about the cross product right now because we don't need it. But the first and easiest way to evaluate a dot product is to take the magnitude of each vector and the cosine of the angle that exists between them. So if vector A is pointing this way and vector B is pointing this way, theta is the angle between them, and that's the angle that has to go into the cosine. Well, why? Again, excellent question. Why the cosine? And back in those previous classes, you probably had an answer like, well, that's just the way it is, or that's just the way the dot product works. Well, none of that here. We're actually going to show why we have the magnitudes and specifically the cosine. And to do that, we're going to go back to this equation right here. You'll notice I don't have the little vector hats on this right now. And that's because the only way that I would be able to get a scalar quantity for energy is if these were not vectors. So I've kind of just glossed over the entire vector math requirements here, and all I have are the magnitudes of these two vectors. So let's bring that vector directional aspect back into the discussion here. And we'll do that with an example problem. If I take a force of magnitude 20 newtons, and we apply that force as this mass displaces over 5 meters, well, this is our definition for work so far. It is not the correct definition. Oops, looks like I got to plug in my computer here. That's why the screen was getting dark. There we go. So this is not the correct definition. We're going to modify this in a couple of minutes here. But let's just plug in the numbers. We have 20 and 5, and that makes 100. Work is a measure of the change in energy. Energy is measured in joules, and so there's 100 joules worth of work that is done by having this force work over that displacement of 5 meters. Let's take that same magnitude of force and that same magnitude of displacement. Getting too close to the bottom of the screen here. But now I'm going to apply that force straight up. How much do you think that force is going to contribute to getting that mass to move to the right? And right now might be a good time to introduce some reference frames for these problems. In the first problem, well, it makes perfect sense. I have this force pointing in the positive x direction. I would definitely expect to see some displacement in that same direction. But now I'm applying this force in the vertical direction. I wouldn't expect this force to move the mass to the right. And so the work that I should expect to be done in this case is 0. that force shouldn't be contributing any work. Same force, but now I'm going to apply that force at an angle. And we have the same displacement. Would that force contribute work in moving the mass along the displacement of d? In this case, you'd say, well, yeah, a little bit. But that's because this force has components along the x and the y directions. And the x component of this force, well, it's pointing in the same direction as the displacement. We would fully expect it to contribute some work. But the y component is pointing in a completely different axis. We wouldn't expect that to provide any work to us. So in this case, we actually have both of the previous examples showing up together, but it's only that horizontal component of the force that is going to contribute to the work that is being done. What is that horizontal component of force? Well, if we look at our force, the force vector and the component along the x direction, there's some measurable angle there that we could call theta. And that means that the x component would be f cosine theta. That component of the force could then be applied along the direction of d, and it could provide some work. Question is, how much work? We know that F has a magnitude of 20. We know that D has a magnitude of 5. Well, what's theta? Well, theta could be anything between 0 degrees and 90 degrees. Those are the two extreme conditions that we had up here. But I'll go ahead and say that this is 30 degrees. Cosine of 30. $20 times 5 is 100. Then we have cosine of 30, and that's going to give us 86.6 joules of work. Well, does this look kind of familiar? Does this look kind of like what we were expecting to find with our dot product? Because we have the magnitude of both vectors. We use the magnitude of force, we use the magnitude of displacement, and we had a cosine theta relationship. But here, theta is supposed to be the angle between the two vectors. What was theta down here? Down here, theta was the angle between the force vector and the positive x-axis, but what's the difference between the direction that our force component is pointing versus, still too close to the bottom of the screen. What's the difference between that and the direction that our, I really hate this stylus, and the direction that our displacement is pointing? Well, if I were to shift this displacement vector up, maybe if I drew that displacement vector at the same place as what the force vector was originating from, well, now we can see that that theta value is the same theta value that exists between the force vector and the displacement vector. And this is the definition of the dot product. the cosine theta is actually telling us what component of the force exists along the direction of our displacement vector. And we can now write this as the dot product of the two vectors f and d. We can evaluate that dot product by taking the magnitude of each vector times the cosine of the angle that exists between them. If we do that, we get the same outcome, 86.6. But this dot product method will work for any theta value. In fact, it will help to justify the two values that we got up here. Let's take the first case where our force and our displacement vector were running parallel to each other. The work done is F dot D, which is the magnitude of each vector, times the cosine of the angle between them. Force is 20, displacement is 5. The angle between the two vectors, they're running parallel to each other. Parallel lines have an angle difference of 0 degrees. Cosine of 0 evaluates to 1. 1 times 5 times 20 is 100, so that works. For the next one, this is the case where our force and our displacement vector were at a 90-degree angle with respect to each other. Work is F dot D. We evaluate by taking the magnitude of each vector times the cosine of the angle between them. Now, regardless of the magnitudes of these two vectors, what's the angle relationship between these two vectors? It's 90 degrees. And cosine of 90 is 0, and so it really doesn't matter what this product is because we get 0 work. Our equation for the dot product works for any theta value. Well, we've only seen theta values between 0 and 90 degrees. Is it possible that our force vector could be pointing somewhere beyond 90 degrees? Sure, if you want to. Trying to draw this displacement vector. My stylus doesn't want to cooperate. Here we go. That's better. We'll keep the same two magnitudes, 20 and 5. And we want to evaluate this dot product. We want to see how much work this force is going to do. Okay, magnitudes and cosine of the angle between them. We'll go ahead and put in a value. We'll say that this angle difference is 120 degrees. Back in calculus and trig, you might remember this. Oops, got that wrong. This expression, it's shorthanded to say all students take calculus, but what this does is it reminds us of which trig functions are positive in the different quadrants. So here all of them are. In the second quadrant, only sine, third quadrant, tangent, fourth quadrant, cosine. And so if I have an angle that exceeds 90 degrees, then I should expect the cosine, well, the only thing in second quadrant that's positive is sine, so cosine has to come out negative. And that means our work is going to come out negative. That will be evident when we Put all of this into our calculator. 20 times 5 is 100, times the cosine of 120 is negative 50. We have negative work that is being done. What does that mean? Well, work is the change in energy. Oops, sorry, I don't know why I put a angle there. That should be 50 joules. Work is a change in energy. Well, this says that the energy is dropping. The energy is being reduced. What energy are we talking about? Well, so far we only have kinetic energy, and kinetic energy is the energy that is associated with the motion of this object. Let's take a look at the components of this force and see if we can figure out why we're getting a negative work. We have one component of the force that is pointing in the negative x direction, and we have a component that's pointing in the positive y direction. Put those reference frames in right here. As far as this component of the force goes, that is perpendicular to the displacement vector, so we know that that component's not going to do any work. But this component of the force, it's pointing in a direction that is opposite of the displacement vector. And remember that your force is hiding acceleration. You have a mass that is trying to move to the right, yet you're pulling it to the left. What's going to happen to its velocity? Well, it's going to slow down as it moves to the right because you're pulling to the left. And it will continue to slow down. It will continue to change its velocity. Its velocity will continue to reduce, which means that its kinetic energy needs to drop. The only way that can happen is if we take some of that energy away. We have to do negative work. And so it is very feasible that you could have a force in your system that is doing negative work. But at the same time, you could have other forces in the system that might be doing positive work. You could have a force in your system that is doing zero work. So all of these forces, considering all the different kinds of work that they can do. Well, some forces can do positive work, some forces can do negative work, some forces may do zero work. But at the end of the day, the work that is done is a scalar quantity. And we can just add these directly together. We don't have to worry about the vector components of the forces and the displacements anymore. In fact, I could probably get away without even having to use reference frames for these problems. If I remove the reference frame from this first example, do you really need me to tell you that this is the positive x direction for you to be able to carry out this dot product? And the answer is no. The only thing I need to know is what is the angle relationship between the directions that these two vectors are pointing. Well, I don't need that x-axis to see that they're parallel to each other. And so I'll still get 100 joules of work being done in this case. For the second case, do I really need this xy axis over here to tell me that there's a 90-degree angle between the two vectors? And again, the answer is no. I don't really need that reference frame there. I just need to know the angle between those two vectors. Likewise, for the third case, do I really need this xy axis over here, or do I just need to know what the angle is? And as it turns out, I just need to know the angle that exists between those vectors, and I can get the work. Once I have the work, that's a scalar quantity. I can add scalar quantities together, and I can produce the network for the system. So I much prefer to look at the individual forces and find out the individual work that they do. I add those up, I get the network for the system. I can completely bypass having to take a sum of forces for the system. And now that we have the net work, we can apply that net work to the change in the kinetic energy for our object. We're going to stop the video here because this is quite a bit of information to digest for one video. So when we come back, we'll look at an example problem where we're actually going to apply multiple forces to an object, find out how much work each force does, combine those into a network, and then see how that network changes the kinetic energy of our object, and in turn, if the kinetic energy changes, how the velocity of that object is going to change. It sounds a bit involved, and at this point you might be saying, well, I'm pretty comfortable using the kinematics. Can't we just keep using the kinematics? You can, but there's going to come a point where I think you'll actually see that the process of using energy is a lot more efficient and it's a lot quicker. We just have to see a couple of example problems worked out, and then as we get used to it, I think you'll see that things are going to click, because with energy and work are scalars. They don't care about direction. All they care about is where you are and how fast you're going. We don't have to worry about any of that vector notation anymore. With kinematics, you still have to concern yourself with vector notation, because all of these terms are vectors. So it's your choice, really. Whenever you're doing any of these physics problems, now that you have a choice, it's always good to have more than one method of solving a problem. But do you want to use the method that involves scalars, or do you want to use the method that involves vectors? And I think you'll ultimately agree with me that being able to use the scalars is the way to go. All right, so I'll see you at the next video.